Hello everyone, I am Gizmo Crusher 17, and today I have a interesting series. This is actually the beginning of a series that I'll be releasing. This series will be going along the adventure of me creating a 24 by 24 by 24 Redstone computer cube. Now this cube is a idea that I got from a YouTuber who also does Bedrock videos. His name is The Darkness 344, I believe, and he built a 30 by 30 by 30 cube. Now, this piqued my interest, and I decided to tackle the project to make a smaller, much more compact machine with its own display inside. The Darkness 344 actually had display not inside the computer itself. He had it detached, but I would like to put our own display into this cube. And that will actually be what we go over today. So today we go over the display designs, how binary works so that there's a better understanding for people who don't know how it works. It's very easy to understand, so don't get overwhelmed by it. I think I actually learned this language within about a week, but we won't go over everything in a week. Don't worry. If you already know this information, then you can go ahead and skip to the timestamp that I'll have in the bottom right hand corner. However, that timestamp will actually be going to the explanation of these three components, the reason why I chose them, the effort it took to build them, and so on. And then obviously next video will be the tutorial on everything. I'm going to go ahead and start off with pausing right here. So you can go ahead and pause the video if you'd like to read all these signs. This is the overview of what I'm going over today. Alright. To start off, how does binary, I guess, work? Because that can be a very confusing question, especially when you start adding more variables to the way that binary works. There's a whole bunch of different complex ways it can work. But I'm going to go over a very simple explanation of it. Right here I have I guess, truth table for binary values. To clarify what you'll be hearing later on in the future, each one of these lamps represents a bit, and you will also hear 4 bits and 8 bits when talking about adders or ALUs or other parts of a system. And that is important because there's vast differences between a 4-bit system and an 8-bit system. But this right here is 1 bit. This 1 bit corresponds to 1, this bit corresponds to 2, this bit corresponds to 4, to 8, to 16, to 32, to 64, and 128. As you can see, the multiplication of numbers is linear. I like to call these numbers the prime numbers because you can get a derivative of any number out of these numbers. So by adding together, let's say 16 and 1, well, you just got 17. Adding together 16 and 8, you got yourself 24. Right here I have an example. I did not mean to do that. Right here I have an example number, 84. How do we go about getting 84 written down in binary? That's actually very simple. You go to the next largest number closest to 84, which will be, in this case, 64. If we go to 128, obviously it goes over the number, and that's not accurate. So 64, but we still have 20 values, 20 numbers to go before we reach 84. Well, then we just go over here and select 16. Now we only have 4 more values. Well, that's very handy because there's a 4 right here. So now 64 plus 16 plus 4, or 001, 01010, is 84 in binary. That is the binary value of 84. Now you're like, well, what's the point of all this if you have to add the numbers together, and how am I supposed to remember the numbers? Well, it's easy. When reading binary, you don't read right to left, so don't think that this is the number 1 and that's the number 128. It's always from right to left. So you always read from 1 2, 3, 4, 5, 6, 7, 8. You don't read from this way like you read a book. And with that knowledge, you're able to easily put up the number. Now, the way that the numbers are formed is actually very simple. They are clearly multiples of each other. So 2 is a multiple of 1, so 2 times 1 is 2. 2 times 4 is, well, actually 2 times 2 is 4. 4 times 2 is 8, and then 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. And 64 times 2 is 128. It's very simple. Now, when I said that there were significant differences between 8-bit systems and 4-bit systems, there is good reason for that. When you have an 8-bit system, you're able to do a whole bunch more calculations. You're able to go higher numbers and higher values into a calculation. You can get more accurate outputs. Whereas with 4 bits, you're limited to about 15 digits. 16 if you count the 0. But if you go with 8 bits, you have 255, 256 counting the 0. So clearly there's a huge difference, massive difference of values between 4-bit and 8-bit, which is why I prefer to have an 8-bit system in our computer. If I want to do the Fibonacci sequence in our computer, with 4 bits, the computer would only be able to go to 13 because 21 exceeds the 15 limit that we have here. But if we have 255, wow, my brain just died. 255, then, you know, we could go a lot higher with the Fibonacci sequence, and that's actually the goal of this computer, is to be able to accomplish that mathematical equation. All right, so we've gone over that. Let's go over our next topic, which is the way binary is integrated into circuitry. This right here is called a decoder. Now, this decoder is able to take binary values and revert them into a single output without smearing. Smearing is when data between points gets, well, smeared. For example, actually, yeah, this is a good example. So if the system wasn't here, this system is only supposed to look for the binary value 1001. But if we didn't have a system, then this output would activate no matter what the pattern was. And we wouldn't have a discernible output. We wouldn't have any way of pinpointing, certain events of a Redstone contraption or a computer. So this decoder is allowing us to pinpoint patterns in Redstone signals. And these patterns is called binary. Binary outputs from our adder, which will be reviewed in the next video, or actually the video after the next video. So the next couple of videos. The output from that adder goes into this decoder. And if the output is a pattern recognized by the decoder, then we have an output of at one point or another. And there's a total of 10 different decoders for this machine to go through. All the digits between 0, 1, and 9. So, oh yeah, and this Redstone lamp represents this piston down here, which activates a pre-programmed digit in this ROM package for the display. More about this and how it works in the next video. For sure, the next video. But anyway, so this means we can, put in any other combination of inputs and not get an output. We only get an output when there is the correct pattern or the correct sequence of binary digits. So 1001 in binary is 9, which, as you can see, is right here, and the same pattern that you can see in the decoder up here is shown right here. These green wool blocks represent 1, and this represents 0, as you can probably clearly discern. And these blocks in the contraption represent 1s, and these torches represent 0s. Now let's go over this display. This display took me several days actually to compress into a 3-block wide contraption, and it's pretty tight. It's actually very tight. That does not belong there. And you know, this, I'm proud of this entire display contraption. You will see the entire machine working in a second. I'll bring you over there to show you how all of the components work together. But for now, a few features that I want to explain about this display. 1, it's very small. 2, it has its own implemented feature. When there is no input at all in the machine, it goes into standby mode, which is this dash right here. So if this display is not receiving any sort of data, it turns on standby. And you can turn off standby to completely turn off the computer or whatever by activating that data line right there, and there you go. Other features, well, it's fast. Did I already say compact? I'm pretty sure I already said compact. And it fits very well with this ROM module. This is able to hold 10 digits, so all the digits between 0 and 9. Now the way that this works is fairly simple. I'll go over a quick overview. These redstone blocks connect with the redstone dust right here, which carries the signal all the way down to the display. And occasionally we break up the signal with repeaters, and it gives off a pattern that we can decode using that display. Alright, so now that we've seen all 3 parts and we basically know how they work, let's go and see them in action. Now, you will definitely recognize this formation, because we already have one over there. This is a older version of the cube that I was experimenting with, and it does kind of work, but there are a few kinks I need to get rid of, and it just was easier to start over. So, as you can see, it's actually pretty fast. If I was to input any number between 0 and 9, which actually right now it's 0 because there is no value in there right now, we can actually go over here and let's do the digit 7. So 1 plus 2 plus 4 is 7 in binary. We can go ahead and see that work right there. So now we have 7. Now I want to look at 5, so that will be disabling the 2. So 4 plus 1 is 5. And there we go. Now this is by no way an adder. By no way an adder. That's absolutely ridiculous. The adder is right here. And this is actually the 8-bit version of the adder. And it's pretty hefty, but this all right here is bogus stuff. You honestly don't need it there. Other stuff will be going there instead. The true masterpiece of this area is this section right here. You will be hearing the phrase space efficiency quite a bit in this series, because when it comes to using the space well in this computer, we have to make things as compact as possible and make sure every contraption uses as much of the space as possible. I guess a good example is that each bit or module of this adder has 11 blocks of unused space, which is significantly better than the 31 blocks that this module does not take. I went through a whole bunch of different adders and found the ones that were the best, and my own design was actually the best space efficiency wise. Speed wise, not very much. Our computer is not going to win any speed awards. Alright, Last but not least, a little overview of the game mechanic that we use. A little disclaimer, this channel is only a Bedrock channel. 90% of the features that we use would not be applicable for Bedrock or Java. I hope I didn't say it's only Java, it's only Bedrock. For example, if you were to do this in Java Edition and have a redstone block above a piston, the piston will be stuck in the upright position. It will push the redstone block upwards. It's just a bug powering of a piston. It's very weird. And you would also not be able to turn off a redstone torch by using a piston of any sorts, which is what I'm going to go over right now. So to better understand the way that these contraptions will operate, we need to know how a piston can be powered to turn off a redstone torch. Now, a piston can be facing any direction for this to be able to work. But you cannot turn off a torch or power this piston from the face. So if you power this block, that powers the face of the piston. But that doesn't power this torch, so that doesn't power anything, as you can see. If we power the piston itself, we clearly have an output. If we power below the piston, we get an output. And if we power the side of the piston, we get an output. So that's basically how this works. And we can definitely use this contraption without obsidian. But for compacting purposes, I do like to use obsidian, so we have blocks to place other redstone components on. Like I just mentioned, you cannot power or use this functionality by powering the face of the piston. So we could have contraptions that look like this. Yeah, there we go. And be able to send redstone signals over the same contraption, but not interfere with anything, which is pretty cool. I have to admit, it's pretty cool. Now, with this functionality, we're actually able to make a whole bunch of different logic gates. Over here, I have a whole list of logic gates that I've was able to find online and convert to this game mechanic. I'm not going to call it a bug because honestly, it's a game mechanic. We don't have the ability to turn off or use redstone components by powering a target block, unlike Java Edition, unfortunately. So right here, I do believe this is a OR gate. I should have had this one labeled. I think that's why I'm broke on this one. This is a NOT gate, so as you will see that these operate very similarly. Now, traditionally this would not be used because it takes up an extra block of space, but when it comes to fitting this into different areas, tight spaces, when it comes to putting redstone dust on top of blocks, this would be useful. This is a AND gate, so when both inputs are on, does it give an output? So 1, 1 gives off a 1, 0, 1 or 1, 0 gives off a 0. Alright, and this does the exact same thing, so 1, 1 gives off a 1, 0, 1 gives off a 0. This is an OR gate, there's no way to compact that anymore, so this is an XOR gate. So this allows us to, this is actually, I think, the first component to a adder. With a few modifications, you can make this into a half adder. But with a 0, 1, you get an output. But with a 0, 0 or a 1, 1, you get a 0 as an output. You can see that right here. Now XOR stands for exclusive OR. This is a full adder, which probably will be explained later on down the road, the reasons why I did not use this contraption. And big hint, the reason, space efficiency. This is a half adder. So it has an AND gate at the end of an XOR gate, making it a half adder. And this right here is a XNOR, which is this literally. This is an XNOR. It's a half adder. So those are the gates that I was able to convert into our bedrock game mechanic. Alright. So that is it for today's video. If you enjoyed this video, if you learned anything, please leave a like. If you really enjoyed my videos, I would really appreciate a subscribe. It wouldn't hurt, and if you wanna be able to watch any future videos, it's free to subscribe, so it doesn't hurt anything. But anyway, guys, this was Gizmo Crusher 17, and see you guys in the next episode.